Welcome to this video on supernova explosions and using them as distance measurements in the universe. So firstly, what is a supernova? Well, it's the violent end to the most massive stars we have in the universe. So when these very large stars cease fusion in their cores, they have no way of holding themselves up against their own gravitational force, and they collapse and then rebound, causing a supernova explosion. So here you've actually got the Crab Nebula, and then in the center of that you've got the remnants of one of these old large stars, which is a neutron star or pulsar, and you can see zoomed in there you've got the actual material around that pulsar. But there isn't just one type of supernova explosion. There's various different types. So the two main ones really are type 2. So type 2 is when a very large star comes to the end of its life basically, and it undergoes a supernova explosion when there's no longer any energy generation in its core. And then you have the type 1a. Now the type 1a involves a white dwarf star and a red giant star, and they're quite specific. So they kind of occur pretty much the same each time, whereas a type 2, what you get depends on the size of the star when it ends its life. But it's the type 1a that we're really interested in. So in this video, it just shows you on the right hand side, you've got a small white dwarf star, and it's pulling material off a red giant star nearby. And then at some point, it goes supernova. And that supernova that results from that system is a type 1a. So it's a very specific system regarding a binary of a red giant and a white dwarf. So that white dwarf pulls the material off, and then it gets to a certain size or mass, and then it'll have a supernova. Now, white dwarf stars are about the size of the Earth, but they have a very large mass. So they're about the mass of the Sun, and a little bit less. But they have an upper limit of about 1.4 solar masses. So once they get beyond 1.4 solar masses, they're no longer a white dwarf star. They have enough gravitational force to collapse them further, and they can actually become a neutron star. So if you have a white dwarf star that's got a mass greater than that, it's not going to be a white dwarf star, it's likely going to be a neutron star. So there's this limit, this 1.4 solar masses. And that's quite important for these supernova explosions. So on the left hand side here, you've got an image taken where you've got a white dwarf pulling material off this red giant, and then you've got an illustration on the right to give you a bit more of an idea. But at that point, as it's pulling that material off, it's growing in size, that white dwarf. And once it gets to about 1.4 solar masses, it approaches the ignition temperature of carbon, and then it undergoes a thermonuclear reaction, which is basically a runaway reaction, and it just goes into a supernova. And at that point, because it's always at the same mass, it's always with the same absolute magnitude or luminosity. So we know the energy involved each time. So that's really useful to know. And if you know how to calculate a distance to a star using this particular equation, if you're not familiar with that, you can check out one of my other videos that introduce this. But you can work out a distance to a star if you know its apparent magnitude and its absolute magnitude. So the absolute magnitude is the brightness of an object from a set distance, which is about 10 parsecs. And the apparent magnitude is how bright we see it from Earth. And the difference between the two, you can work out how far away it is. Now we know how bright a supernova or a type 1a supernova should be from a set distance, and we can just measure its peak apparent magnitude to get the distance to it. So here we've got an example of one. So on the right hand side you can see you've got a galaxy and what looks like a very bright star, but it's actually a supernova. And if you think about the fact that a galaxy is a collection of billions of stars, you've got this one supernova which is outshining all of them. And then this plot is called a light curve. And a light curve is just the brightness of an object over time. So on the y-axis you have your apparent magnitude as measured from Earth, and then on the x-axis you've got your time. And you can see that actually the supernova increases in brightness, and then it peaks, and then it will slowly decrease over time. So from that light curve, we can work out its maximum apparent magnitude, and we can then put it into this equation here. So if we actually look at this particular one, we would say it's probably about 12, magnitude 12 that it's peaking at. We know that the absolute magnitude of these type 1a supernovas is minus 19.5. We can then put those values into this equation here. So just to highlight the bit we need for the equation, it's this top bit, the actual peak. This is the maximum apparent magnitude on the light curve, and that corresponds to the peak absolute magnitude of minus 19.5. Now, if we go and put that into our equation, you should end up with approximately 20 million parsecs, this particular supernova, as an example. So have a go yourself, see what you can get. But these supernovas are very good for calculating distances to other galaxies, because we can't normally resolve a single star, but because these supernovas are so bright, we can actually use them for further distances to other galaxies than that. So thank you for watching, and if you enjoy, then check out some of the other videos.